Hello and welcome to RF Magic's flight readiness review. So we'll start with our mission summary, which hasn't changed since PDR pretty much. So our primary mission is still to use standard sensors to measure altitude, longitude, and latitude. Our secondary mission is to use 2 ground stations, a rocket, and 2 CANSATs to create an aerial mesh network. And our tertiary mission is to use additional sensors to gain information to aid in the development of our next rocket, which will be Stratosphere 2, which will hopefully be entering into Mach 23. We will now go over the mission summary and final design overview for the launch vehicle and payloads.
Our launch vehicle, Stratosphere 1, is intended to carry a payload of 2 500-gram CANSATs to an altitude of 1 kilometer. Throughout the flight, Stratosphere will be recording and transmitting telemetry, including altitude and acceleration, to help the team understand the flight and aid in the development of Stratosphere 2. The secondary mission for this flight is to participate in a 5-node mesh network to relay a message between 2 ground stations without a direct line of sight. It's our critical design review. We've had to change our motor, unfortunately, due to a stock issue on rockets and things. The motor presented in the critical design review was the 548 I242 white. However, we've had to switch this to the 601 I350 Smoky Sam. This motor has a much higher impulse, so we've had to redesign a few parts in the aft of the rocket to accommodate for this. The thickness of the phenolic tube we were using from the rockets and things was unknown until lately. We've had to switch our supplier for the phenolic tubes to Black Cat Rocketry. They provide the thicknesses exactly. So now we know the inner and outer diameter and can implement that in our computer-aided design. We've had to move some things around in the nose cone as well. Our avionics bay has been completely redesigned to help keep all of our avionics safe from the descent system and ejection charges. And we've removed the need for black powder as our new motor is reloadable and has an ejection charge built in. So we can use that motor multiple times and use a delay to eject our payload for us. Our new I350 Smoky Sam motor has 51 Newton seconds more impulse than the old motor, the I242 white. We've carried out launch simulations again, presented in the next slide, to reflect this change. Below, at the bottom of the slide, we're showing our thrust curves. So on the left-hand side, we have the I350 Smoky Sam, and on the right-hand side is the I242 white. You can see the Smoky Sam has a much higher peak thrust of 400 newtons as opposed to 300, and a burn time of 1.9 seconds as opposed to 2.4. We carried out our simulations in the same conditions as we showed in the critical design review, and in a worst case scenario configuration, so that's no payload on board for maximum altitude. However, the drift rate would stay the same. In a 5 meter per second wind, we would like to launch at a 5-degree angle to limit the load on our parachute, as well as to keep drift down to about 250 meters. In a 10 meter per second wind, we would also launch at 5 degrees, again to keep the loads on the parachute minimal. However, in a 15 meter per second wind, we'd need to launch at a 10-degree angle to keep the drift within the territorial boundaries. On each of these graphs, you'll see a peak on the top right side of the curve. That's when parachute deployment occurs and when the falling of the rocket is overtaken by the wind dragging it the other way. When the launch vehicle is fully loaded, the static margin increases, which increases the lateral velocity, therefore the load on the parachute when it inflates.
Hi there, I'm going to go over for you the changes that we've made to our avionics and nose cone assembly. One of the main changes that we've faced in CDR was a slight change in PCB mounting point position, and these are now placed in a more reasonable spot and means we also had to redesign the mount for them with necessary clearance. Another new addition was a 5mm longer battery, which needed extra length in order to mount properly. The design of the avionics mount in the nose was derived from the mount used in the CANSATs, so they're now also quite similar. The nose cone now includes a rear retaining piece to encase the avionics and separate them from any ejecting pieces. The next change is the use of U-bolts now instead of I-bolts for design sturdiness. The larger switch which we're also using will now be bolted into the retainer and given enough cable length for accessing the avionics with no problems. The retainer piece has been printed with 2 thick prongs, which will hold the avionics in place. And there are now also 2 small aerodynamic holes in the side of the nose, which will allow the likes of pressure sensors to read accurately during flight. Also, the length and diameter of the nose remain unchanged from CDR.
So here at RF Magic, we'll consider this mission a success if we can successfully launch and recover Stratosphere 1, our first high-powered rocket, if we can launch a 1 kilogram payload to an altitude of 1 kilometer, if we can collect data from the vehicle all the way from liftoff to touchdown approximately 2 minutes later, this can either be stored on our SD card on board or transmitted directly to our ground stations. If the launch vehicle participates in the mesh network, as mentioned on our mission statement, and we'd like to inspire a new generation in the United Kingdom, specifically Scotland, to take an interest in rocketry.
Now on to our payload for the competition. Our payloads, now named Bod 1 and Bod 2, will be ejected from Stratosphere 1 at apogee. On their descent, they will measure altitude and GPS data. In flight, they will help build an aerial mesh network, allowing communication between 2 ground stations without direct line of sight to each other. Gathered telemetry data will be stored for collection post-flight. I'm now going to take you through a few of the notable mechanical updates for our payloads. So the eye bolts, like the nose cone, have been replaced by U-bolts. The PCB shape is altered, so mountings have been reworked to fit the PCB. The battery holder and PCB mounts have been extended for holding the longer battery. The GPS mount has been reworked to fit slightly different GPS shape, and the 2 of the threaded rods in the CANSAT have been cut into 2 pieces, which allow more internal room and less clipping of real-life parts. So I'm now going to outline our payload success criteria. Our first point is the successful deployment and subsequent measurement of GPS, altitude, acceleration, and pressure. The next is creation of a successful mesh network allowing communication between 2 ground stations. The next is data stored for collection to assist in the development of subsequent rockets and payloads. I'm now going to take you through our finalized designs for our launch vehicle. Here's the overview of Stratosphere 1. The idea of our launch vehicle has changed very little since CDR, only iterations of parts and sizes and updated masses and positions are different. On the next slide, we have a close-up of our new launch buttons. As we could not source the correct size in the UK, we decided to design our own that were compatible with the real list on the guidelines. So here's them. Next is a close-up of our motor retainer. This was bought from Black Cat Rocketry and is compatible with their motor. It's also a lot smoother than the previous bolt-in method, now utilizing a screw thread to tighten the retainer instead of just bolting it to the rear centering ring. The thrust section as a whole of the rocket remains mostly unchanged, with the only differences being updated fin sizes, these new 3D printed launch buttons, and the U-bolt replacement that you can see at the furthest forward centering ring. To touch on launch site construction, we're currently on track to have a complete launch vehicle by the competition date, with some time for wiggle room for any eventualities that may occur during the construction. The only on-site construction we'll be doing will involve ensuring the relevant shock cords are fastened, our ejection system and payload are integrated correctly, and fitting the nose cone to the top of the rocket before launch. Now I'm going to take you to the final design of our payload. This is an overview of our CANSAT design here. The overall design of the CANSATs also remain quite similar to the CDR, and the only deviations from the CDR are as follows. U-bolts are now being used over I-bolts. There is less wiggle room inside the CANSATs because of longer batteries. There's a slightly longer total length from the U-bolts being used. Parachutes will now attach to U-bolts via carabiner clip, so they're easily detachable after they've landed. To keep the CANSATs separate on launch, small spacers are going to be used as before. For construction at the launch site, we're also on schedule to having a completed construction ahead of the competition, once again with a time margin for any eventualities that we might encounter. The construction on site, though, may involve fitting the electronics to the internal structure and securing this all within the CANSAT shell should we need to transport the CANSATs disassembled. After that, the parachute will be clipped onto the payloads and it can be put inside the launch vehicle.
As far as our avionics go, since CDR, we have decided to expand our use cases of our PCB design, which we have decided to name the Shaman board, into our ground stations as well. This is because we have demonstrated that we can use our microcontroller to expose its UART interface into the USB port, allowing us to control the radio externally. As you can see on the picture, our PCBs have been fully manufactured and assembled. And unfortunately, we had to skip version 2 due to manufacturing delays. but thanks to our planning at CDR, we were able and are still on track to bring V1 to full functionality for Mach 22. We have identified most of the critical design errors and are either in the process of or have already rectified most of them, as will be shown in more detail in our testing campaign. This makes us very confident in the capability of our board, and we think that it will be fully functional and ready for the launch campaign.
Moving on now to the recovery subsystems. The recovery system of our launch vehicle has been developed further from our CDR. One minor change excludes the need for any black powder, as we learned that motors do indeed come with ejection charges. We'll be using this ejection charge from the motor to produce the force to eject all the contents of the rocket. We plan to use Kevlar shock cord, but to be safe, we'll be braiding it to further improve its tensile strength. This will be used in tandem with recovery wadding to shield from the ejection charge heat. Ejection and descent tests yet to be performed for the launch vehicle. Ejection tests will also be tough, as we have not found a source for replacement ejection charges. The recovery system for our payload is much the same as our CDR design as well, with a passively deploying parachute. After the payload is ejected from the launch vehicle, the parachute naturally unfurls and the payload descends. Payload testing has taken place, which we will touch more on in following slides.
So we began the design of Stratosphere 1 in September and have recorded the progression of our design throughout using the PDR, CDR, and now FRR. Unfortunately, the construction stage was delayed, but we're back on track now. The PCBs have been fully constructed, and we hope to have our rocket fully constructed by the end of the week. And the CANSATs have also been fully constructed. We've been using OpenRocket since about January to assess the stability of the rocket as it progressed through its design iterations. And we've also been using it to see how wind conditions will affect drift. This is to ensure that we have an optimal launch rod angle for every allowable wind speed. We've also now begun extensive testing, which will hopefully conclude shortly. At the moment, this has been mostly focused on the electrical side. There's been a lot of range tests using the radio and a lot of other sensor tests that are at the conclusion stage, and we can now focus on our mechanical testing suite. The results and schedule of testing can be found in the appendix of this presentation. Unfortunately, there just wasn't enough time to fit it all into 15 minutes. You can also find our launch procedures in our appendix, as well as our outreach update and our 6 member rules. Again, we just couldn't fit it into 15 minutes.
So we've used OpenRocket to verify our design throughout the competition. Recently, we have corrected for the exact component sizes and masses, giving us a more accurate simulation. Using a back and forward approach between OpenRocket and CAD, we've reached this final design here. Displayed on the left are the key stats of our launch vehicle and its performance with max minimum payload. We're just within the static margin numbers on the guideline document, and our velocity of launch rod is now higher as we're accounting for the full 4 meters of rod. OpenRocket so far has been our main source of in-flight data and will likely remain that way until launch of the competition, because we haven't been able to source any refills for the motor.
As can be seen on the picture, this is the current state of our avionics testing.
So to summarize our conclusions, our major accomplishments in CDR have been finalizing all of our designs and carrying out a significant amount of testing. We've also identified problems on PCBs, and fixes have either been implemented or be in the process of being implemented. Our major unfinished work is, of course, the construction of the rocket, which we hope to have finished by the end of this week. We will also be finalizing code this week and next week, and finishing up the remainder of our testing, hopefully by the end of this week.